Okay, let's see now. Part A, prove this. Excuse me. Okay, so that would be F A1 union A2. That would be F of X, where X is in A1 or A2. Mm, so could I? Yeah, I could split this because I could just say that's f of x, where x is in A1, because it's union. And then here I can split. Yeah, I mean, that's pretty obvious. Um, I'm just partitioning the set into two. I think a bit more difficult would be B, though. Prove that, give an example in which equality fails. So f A1 intersect A2, that would be f of x, where x is in A1 and A2. Um, that would be f of x, and I think we had this earlier. You could say x is in A1 union A2 less, oh, what was it now? We had this as one of the questions earlier. Um, it is only A1, only A1. So that would be A1 less A2. Hang on, I need a bit. Yeah, this is a bit longer than I thought. Let me scooch this to the left. X in A1 union A2 less A1 less A2 union A2 less A1. So it's this union minus this. So because of the less, I can make this set bigger by just excluding the less. Oh, that's not quite right because I want the uh, I want the intersection, not the union. So yeah, I can show it's a subset of the union, but actually that's not quite right. I want to show it's a subset of the intersection. Okay, let me think. Um, X is in A1 and X is in A2. Um, oh, actually, now let me think. What would be the best way to prove this? See, if I kind of just draw it here, what's happening? I can apply F here, or I can apply F here, And then I can apply f here and take the intersect of the result. Hmm. Let me pause and think for a second. Yeah, so maybe I want to say something like this. X is in A1 and X is in A2. And then less the X that's in A1, remove A2, or X in A2, remove A1. I have a space there. So splitting that would be f of x, x in A1, intersect f x, x in A2, less, and then f of x, x in A1 less A2, or A2 less A1. Okay, so let me think, does that make sense? We draw a Venn diagram. So it's all of these, so all the x's here, they get mapped. All the x's here, they get mapped and then intersected. But that's going to be too many. So we have to remove the ones that got mapped from here or here. So I think that's okay. I think that's okay. And then if you drop the removal, you've made it bigger. Um, I think that's okay. Give an example in which the equality fails. So when you don't get an equals. Okay, let's try and keep it simple. A1 equals, maybe I could just go with, I don't know, 2 points maybe? Or actually I should use the same letters. X equals, let's just keep it really simple. How simple can I make it? X equals X, Y equals Y. Oh no, I need to have subsets, so I need to go with at least 2, X1, X2, Y1, Y2. Oh, but I need an intersection. So what about if I make them the same? And what about if I had f of x is just equal to x? So f of x intersect y, that'd be identical. So it'd just be f of x would just be x. And then f, oh no, I need subsets. Okay, so let's see. Okay, so if I have, let's see, f, then I need a subset. And I want to show that that's not equal to f particular subset intersecting f particular subset. What about if I went with x1 and x2? No, x1 and yeah, maybe I could just go with x1 and x2. So then that would be f of the null set, which should become the null set. And then this one here, f of x1, f of x2. That'd be x1, x2. Now that'd be the null set as well. So I need this one to be a little bit bigger. What about f of x1 equals x? What about f of x always equals x1? So this would be x1 intersect x1, which would be x1. And then this one would be x1 intersect x1. No, that'd be the same. Oh, okay, let me pause and think more for this. No, I'm right, because x1 intersects x2 is the empty set. Because there's no intersection here. So it'd be f the empty set, which would be the empty set. Okay. So this one here, that'd be x1 intersect x1. That'd be x1 then. I think so. That example would work. x1 intersect x2 is empty. F of empty is empty. F of x1 intersect f of x2, that's x1. Yeah, that's an example when they're not equal. But it's definitely a subset. That is a subset of that. It's just not an equal. It's not equal in this case. Okay, so I'm happy with that now. Prove C. Prove F inverse that equals that, where F inverse B is that. Okay, F inverse B1 union B2. That will equal F inverse the set X in X, prefer to write it this way, X, where X is in X, and F of X is in B. Well, actually, in this case, it's not B, it's B1 union B2. Okay, so it's all the x's in the domain of F, whereby F of X is in this set here. Okay, so I guess because of the union, there's no problem if I say, if I partition this as X, X in X, and F of X is in B1, and then union F inverse X, X in X, and F of X is in B2. Can't see why there'd be any problem with that. So I've just yeah, because what's happening here is either f of x is in B1 or B2. So I've just split it into the two possibilities. So that's F inverse B1 union F inverse B2. Okay, so that makes sense to me. D now, that'll be a bit harder. Whoops. D. Let's have some coffee. F inverse B1 intersect B2. That would be F inverse. Oh, hang on, did I write something wrong the last line? Oh, the last proof. Oh, yeah. Sorry, I didn't need to write the F inverse there. Sorry about that. Yeah, because F inverse is all the x's, whereby f of x is in this. Yeah, so I didn't need to write the F inverse. Sorry, forgot that. Okay, now it should be okay. Okay, now back onto D, sorry. F inverse B1 intersect B2. That would be all the x's, where x is in x, and x is in B1, and x is in B2. Okay. Let's see now. So it's all the x's. There's B1. There's B. Maybe if I draw this, it might help focus our minds. So we have x, and in x there are two subsets, A1, A2, and then there's y. And then we can have it like this as well. There's B1, there's B2. So F okay. X needs to be in B1 and B2. Oh, sorry, not X. F of X. So we have X in B, F of X in B1 and B2. So that's all of them here. But the X has to be in the domain X. It could be anywhere. So for all the points that map like this, for example. Yeah, okay. So what I can do, I can say, this looks the same as saying X is in X, F of X is in B1. So that would map all the points here to all the points in B1. And then I can think about all the points here that map into B2. So that would be X is in X, and F of X is in B2. But you want both the green and the blue. So we have to intersect the results. So yeah, that makes sense to me. F inverse B1 intersect F inverse B2. Yeah, that looks okay as well. I wonder if I could have done something with the Venn diagrams in the last one as well. Let's see. Do, 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 do. Ah, it's all right. Leave it. Let's just go on to the last one. And then E, F inverse Y less B1. So that will be all the x's where x is in x, and then f of x is in y less b1. So let's see what that looks like. There's x, there's y, there's a1 for example, there's a2 for example, there's b1, there's b2, and it's all the points here in x that go to y less b1. So that's not in b1. So like, for example, that could be like all these purpley ones here. So that would be like taking up some random point here to like say here, whatever. Yeah, okay, so I can see that would equal all the points in x except where f of x goes to an element in B1. So it's all the points here, except for the ones that would take you inside of B1. So like, that's x, except where the x in x takes you to somewhere in B1. So yeah, again, with a Venn diagram, actually, these kind of make a lot of sense. X less F inverse B1. Yeah. So I think if I had drawn Venn diagrams for all of these, I could have proven them a lot quicker. So that's something useful for someone watching this video to know. Okay.